Good afternoon, everyone. Welcome to this first afternoon session on Android and deserialization. We're going to have 4 talks on these topics, and we're going to start with the first talk on Beyond the Surface, uncovering the unprotected components of Android against overlay attack. So this paper has authors from Hong Kong Polytechnic University, from Washington State University, and Tsinghua University. The first authors are Dr. Hao Zhu and Mr. Shuhan Wu from Hong Kong Polytechnic, but unfortunately none of the authors could make it to the conference. But on the other hand, thankfully, we have here Song Liao from Clemson University, and he's gonna give the presentation for us. I have only one request for you to add, due to this hiccup with we prefer to take the questions offline, so there will be no online questions for this talk, and we're going to use this couple of minutes for Q&A for the upcoming talks. So let's welcome Song for the first talk of the day.
Good afternoon, everyone. My name is Song Liao, and I'm from the Clemson University. Today, I'm glad to help my friends present their work, Beyond the Surface, uncovering the unprotected components of Android against the overlay attack. The authors are from the Hong Kong Polytechnic University, University of Hong Kong, Washington State University, and Tsinghua University. The overlay or the floating window is one of the key UI features of Android, and it allows an app to draw over other apps' windows. It is designed to enhance the user's experience and has already been adopted by many popular apps. Commonly, apps use overlay to provide additional information or functionality without requiring navigation away from the current window. For example, the Facebook Messenger, a popular instant messaging app, creates an overlay appearing on the top of the other app's window to let users conveniently access the received messages. Another popular video streaming app, YouTube, creates an overlay to play videos while letting users interact with other apps. Like one coin has 2 sides, the overlays are also widely abused by some malicious apps to launch attacks that compromise users' security and privacy. It has been reported that attackers can abuse overlay to steal users' private information by monitoring users' input. Moreover, it has been disclosed that overlay can be abused by malware to lure users to allow the consent for performing sensitive operations by covering sensitive widgets. For example, a malicious app can create an overlay on the top of the system's input method to eavesdrop on users' touch events to steal username and password. A malicious app can also draw an overlay on the top of the Allow button in the system's setting app's permission request window, deceiving users into granting permissions to malware. Since system apps implement many security-sensitive functionalities, such as the permission managing to protect users' security and privacy, they usually explicitly ask the user's consent before conducting sensitive operations. Overlay can be abused to lure users to allow consent for performing sensitive operations. So it is essential to protect systems apps against overlay attack. To achieve this purpose, recently released Android system provides a dedicated window flag named System Flag Hide Non-System Overlay Window for system apps to defend against the overlay attack. Specifically, system apps window can enable the flag, short for the HNSOW, to prevent overlays created by third-party apps from drawing over them. For instance, the permission request window can enable the flag to protect itself and prevents malware from abusing the overlay attack. Although this flag can effectively protect systems apps against the overlay attack, it is unknown whether it is adopted by the system apps whose windows need protection. Unfortunately, missing such a protection commonly exists in system apps. Specifically, we find that Google is constantly applying patches to enable this flag in the system's apps windows in recently released Android systems. Meanwhile, over the recent years, a series of vulnerabilities of missing protection against the overlay attack exposed. Partial of them are listed in the table. For example, CVE 2021-0333 discloses that the activity, Bluetooth permission activity in the system setting app was left unprotected against the overlay attack. As a consequence, malware can abuse overlay to obscure the activity for luring users to allow consent to grant phone book read permission to a connected Bluetooth device. We consider that the root cause of these missing protection issues stems from the absence of a proper guideline, outlining which windows of systems apps need protection against the overlay attack. Through reviewing Google's documentation, we can only derive a vague guidance which roughly states that the window for granting permission, the window for approving app installation, and the window for showing a persistent sensor icon or equivalently privacy-sensitive notification require protection against the overlay attack. The vague guidelines misses a large portion of the windows requiring protection. In particular, among the 10 disclosed cases of systems apps windows that miss protection against the overlay attack, the guidance only covers 3 cases. The remaining 7 cases are non-compliant with the existing vague guidance. In light of these observations, we consider that a proper guidelines for determining which windows of system apps require protection is in urgent need. And a systematic approach to identifying unprotected windows is also crucial for bolstering security measures against the potential overlay attack. In the following, I will introduce how we achieved these 2 objectives. To demystify why a system's apps window requires protection against the overlay attack, we perform an in-depth analysis on the windows under protection in the recently released official Android system, AOSP. The process includes 3 steps. In the first step, we find the protected systems apps windows. Since the windows call add system flags, add private flags, or set private flags, and pass the value of flag to these APIs to enforce protection. We analyze these APIs and their arguments to identify the protected windows. In the second step, we study the features of these windows. Specifically, we manually inspect the source code of the identified windows under protection to understand their functionalities. We also review the code modification history to find the potential reasons for system developers to enable this flag. Third, we summarize the common features of protected windows in 3 aspects, including the startability, functionality, and the interactivity. Then common features are treated as the guidance for determining whether a system app's window needs to be protected against the overlay attack. In the following, we will introduce the observations and the findings through this in-depth analysis. In the aspect of startability, we discover that the windows under protection can be launched in 1 step. The windows that can be directly launched, namely launched in 1 step, are more vulnerable to the overlay attack. For example, the activity Bluetooth permission activity, which asks users to grant permissions to the connected Bluetooth devices, can be directly launched by malware. Accordingly, when launching the activity, malware can draw an overlay on top of the activity to deceive users into clicking the Allow button to grant permissions. In this scenario, due to a lack of the context information, users are unaware that they are interacting with the Bluetooth permission activity. Therefore, to prevent such overlay attack, Android system enables HNSOW flag in the Bluetooth permission activity. In the aspect of the functionality, we uncover that the windows under protection will perform sensitive operations. Windows that implement sensitive functionalities, such as permission management, typically require user consent to perform such sensitive operations. Malicious apps can exploit overlay to deceive users into granting the consent, resulting in the security consequences. Therefore, these windows need protection against the overlay attack. For example, the activity Bluetooth permission activity implements the sensitive function of granting phone book read permission to connected Bluetooth devices. In the aspect of interactivity, we find that sensitive functionalities of protected windows can normally be executed with a limited number of user interaction, usually no more than 2. The 2 user interactions include one for launching the targeting window and another one for triggering the sensitive functionality of the window. Windows requiring few user interaction to execute the sensitive functionalities are more vulnerable to the overlay attack. For example, after launching Bluetooth permission activity, it only needs one click event, namely clicking the Allow button to perform the sensitive permission granting operation. Based on these observations and findings, we derive 3 criteria that serve as a guidance to determine whether a window of a system app requires protection. Whether a window can be directly launched, namely launched in one step, whether a window implements sensitive functionalities, and whether the sensitive operations of a window can be triggered by no more than one user interaction. If a window satisfies all the 3 criteria, we consider that the window needs protection against the overlay attack. Based on the guidance, we design and develop a new approach named the OverlayChecker to uncover the windows of system apps that miss protection. This figure illustrates the overflow of the OverlayChecker, which mainly consists of 2 primary components, including the discovery model and the POC creator model. Specifically, the discovery model identifies the windows requiring protection against the overlay attack in each given system app. After identifying the potential unprotected windows, the POC creator model constructs the proof of concept apps for these suspicious windows to help confirm whether they are vulnerable to the overlay attack. Due to the time limitation, here we only introduce the discovery model in detail, which identifies the windows requiring protection through a 3-step process. In the first step, the discovery model identifies all the windows, including activities and dialogues in the given system app that satisfy the criteria 1. Specifically for the windows that can be directly launched by external apps through the intent objects, the model analyzes the system app's manifest file, especially the attributes enable and export of activities that determine whether activities can be directly launched. In addition, for the windows that can be launched by other components in the system, such as the interface of system services, the model analyzes the code of the system apps and the Android framework, especially for the code that start activities and show dialogues. In the second step, the discovery model identifies the sensitive operation executed by the identified window to determine whether they satisfy the criteria 2. Specifically, since windows executing the sensitive operations normally request user consent, the model analyzes the event handlers of the windows to find whether they call sensitive APIs or access sensitive content providers to carry out sensitive operations. In the third step, the discovery model analyzes whether Windows' sensitive operation requires other users' events to determine whether they satisfy the criteria 3. Specifically, the model analyzes control and data dependencies of sensitive operations to find whether the operations depend on other user events. To evaluate whether OverlayChecker is reliable for identifying the windows of system apps require protection, we manually identified protected system apps windows in 4 versions of AOSP and compared them with OverlayChecker's results. As a result shown in the table, more than 90% of protected system apps window in AOSP can be identified by the OverlayChecker. Accordingly, OverlayChecker is reliable for identifying system apps windows that require protection. We further analyze the 6 protected windows that are missed by the OverlayChecker to answer why OverlayChecker fails to identify them. The reason is these 6 windows neither call sensitive APIs or access sensitive content providers to perform sensitive operation. Instead, they conduct operations on file storing sensitive content. In the future, we will extend OverlayChecker to support this kind of operations. To evaluate whether overall checker can uncover the system apps window missing protection, we first apply it to 2 recently released versions of AOSP. In total, 10 unprotected systems apps windows are identified. We have reported them to the Google and assigned with 3 CVEs with high severity. We further investigate the evolution of the defense strategies and have the following findings. We noticed that unprotected windows are gradually patched in AOSP. However, new versions of AOSP introduce extra unprotected windows. Unfortunately, unprotected windows still exist in the latest version of AOSP. We further apply OverlayChecker to 4 commercial third-party Android systems, and in total, OverlayChecker identifies 39 unprotected system apps windows in these systems. Note, we have reported our findings to corresponding mobile vendors and assigned with 2 CVEs with moderate severity from Samsung. In addition, Vivo also rated our protected cases as high severity. From the uncovered cases, we observe that more unprotected windows are found in the commercial third-party Android systems. Meanwhile, we find that the vendors of these commercial Android applications, Android systems fail to promptly apply Google's security practice to their customized systems. At last, I will conclude our work and introduce the potential future work. In this work, we are the first to systematically investigate the vulnerability of missing protection against the overlay attack in windows of Android system apps. We summarize 3 criteria for determining whether a system app's window needs protection against the overlay attack. Based on the proposed criteria, we design and implement a tool named OverlayChecker, and we apply OverlayChecker to 8 commercial Android systems, and it finds 49 unprotected windows, which are vulnerable to the overlay attack. These findings lead to 5 CVEs, and Google and Vivo rated our reported cases as high severity. In the future, we will investigate the missing protection against the overlay attack in the windows of the third-party Android apps. Thanks for your listening, and if you have any question, you can check the details in the paper or send an email to the authors. Thank you.
Let's thank Song.